The Honorable Distinguished Speakers, ladies and gentlemen. Good morning. Welcome to the third day of the second International Conference on Tropical Meteorology and Atmospheric Sciences 2021. First of all, we would like to say Happy World Meteorological Day and thank all participants for the willingness to take part on the conference since the day one until today, the third day. Secondly, we would also like to welcome new participants who couldn't enjoy with us on the first day or the second day. It's been a great honor for me, Janita, to be the master of ceremony and welcome each and every one of you in this Zoom meeting. Before we come to the main session, let's start this by praying first, so the event will run well without any obstacle at all. Pray based on individual beliefs begins. Praying enough? On this day, we have several agenda as follows. The first is plenary session, the second is parallel session, and the third is closing ceremony. Ladies and gentlemen, as you know, from last Tuesday, this conference has provided you plenty of opportunity to discuss, share knowledge and insights. Besides of that, it also a platform for the researchers to share recent findings and knowledge on meteorology and atmospheric science of the tropics, especially over maritime continent. Ladies and gentlemen, it was such an honor to the community to have a prominent of expert international speakers on the second ICTMAS. Now, before inviting the moderator, we will deliver to you a short, brief biography of our moderator today, Dr. Ferdinand from IPB University. So,
Yep.
okay. Hi, Dr. Ferdinand.
Hello.
And now, um, and now we will begin the interactive discussion with Dr. Ferdinand. Ladies and gentlemen, we have the honor to invite Dr. Ferdinand.
Yep. This is Ferdinand. I work for IPB University. Now I was assigned as one of a board of director of Seong Yoo Biotrop, an governmental institution who are working for Southeast Asia. I think that's enough from myself.
So, Dr. Ferdinand, we have the honor to invite you to have the discuss of today. Time is yours. Thank you.
Okay, thank you very much, the host. The name of the host is Nilu Janita. Thank you very much. So, because we have very short time and there are a number of speakers for the second international conference on tropical meteorology and atmospheric science, as we celebrate Meteorological Day, and also there is also Water Days at the same time. So, I want to invite the first speaker, Miss Dr. Sandro Lubis. He is working for now at Rice University. The time allocated is from 7:45 to about 15 minutes. So, Pak Sandro, please, time is yours. Mas Sandro, please unmute yourself.
Sorry for that.
It's
Okay,
okay.
can you hear me?
Yes.
Okay, that's good. All right, good morning, everyone. My name is Sandro Luis. I'm a postdoctoral researcher at Department of Mechanical Engineering at Rice University in Houston, Texas. Today, I'm about to give a talk regarding our recent results on understanding regional scale influence of equatorial wave on extreme rainfall in Java, Indonesia. This work is in collaboration with Muhammad Rehan Restati from ITB University, Indonesia. Okay, so I cannot go to the next slide. So I'm sorry, there's something. I cannot move my slide, so sorry for that. Can you still hear me?
Yep, we can hear you.
All right, sorry for that. So the motivation behind the study is pretty straightforward. Looking back at the two-layer shallow water equation on equatorial beta plane, there exists a general solution of equatorial wave where their eigenvectors follow the quantum harmonic oscillatory behavior. Some example of this wave are known as a Kelvin wave, a equatorial Rossby wave, and also mixed Rossby gravity wave. These three types of equatorial wave are known to play a predominant role in modulating the convection of the tropical regions and also in modulating the perturbation of wind and pressure system of the tropics. So the theoretical structure of this wave are shown on the left-hand side. The color shading indicate the convergence and the divergence of the air mass fluxes. The Kelvin wave is characterized by symmetric perturbation and convection with respect to the latitude and the longitude. The equatorial wave is characterized by the symmetric perturbation in convection in latitude and longitude as well. And Anomaly is characterized by the perturbation in convection with respect to latitude and I'm sorry, I mean the antisymmetric perturbation with respect to latitude and longitude. So from this theoretical point of view, we can see that the equatorial wave really play a predominant role in modulating large-scale convections, and their intensity and frequency really depends on the wave type and phase. So another theory was proposed by Gill in 1980s to describe the steady force dissipative equatorial wave theory on the equator. Using the momentum and continuity equation forced by mass sourcing and diabatic heating, they found that imposing heating that is symmetric with respect to equator can induce a steady damped Kelvin and Rossby wave responses, with the convergence and divergence occur to the east and the west of the imposed heating. So as with the linear wave theory, the forced equatorial wave theory also suggests that the tropical wave can induce large-scale convection of the tropical regions. That indicate that they also can modulate tropical precipitation of the tropics. In terms of the observation, the previous study have also shown that the Kelvin equatorial Rossby wave and mixed Rossby gravity wave can contribute up to 16 to 20% of total rainfall variability of the tropics during the boreal winter from November to April. So there is a growing interest in understanding the influence of equatorial wave on extreme rainfall in terms of the frequency and intensity. Some of the study focus on the regional scale, and some of them looking at the global scale. For instance, the Van der Linden 2016 focusing on understanding the impact of extreme rainfall over Vietnam, and Subin in Landu 2019 looking at the impact over India, and the recent study by Latos 2021 focusing on the impact over South Sulawesi, Indonesia. In recent work by Ferret in 2019, they also show very interesting results in which there is an indication that the equatorial wave can also modulate the tropical extreme rainfall over Southeast Asia. However, if you look at the signal of the Java, it's really clear that they are not significant. So I believe this is likely due to the bias in satellite data set from TRMM. Therefore, there is a need for better understanding the regional scale influence of a Kelvin Rossby wave or MRG on the extreme rainfall for Java Island and understanding the dynamics behind that. So in particular, I'm also interested in looking at how this combined effect of different types of wave can influence the equatorial wave rainfall extreme over the tropics. In order to understand the regional scale influence of Kelvin and Rossby and MRG on rainfall variability over Java Islands, so we use the outgoing long wave radiation data set from NOAA. So the OLR is filtered in time and space following the wave frequency and the wave number for three dominant wave activity over Java Islands, which are Kelvin, MRG, and equatorial Rossby wave. So the OLR is average over a latitudinal band between 5 to 9 degrees south and center over Java Island at longitude 110 east. So the figure on the left-hand side show the snapshot of OLR filter Kelvin, ER, and MRG. So consistent with theoretical theory, with the theoretical equatorial wave pattern perturbations, the Kelvin wave is propagating eastward, and ER and MRG propagating westward in time. So the corresponding phase diagram on the right-hand side show the evolution from the left-hand side for the Kelvin equatorial rosy wave and also MRG wave. So the phase diagram here essentially show the regime transition from the wet phase to the dry phase and transition from the dry phase to the wet phase. So it's very important since we are looking at the regional influence. So these indices really describe the variability of equatorial wave amplitude over certain regions. So these different phases we can use to perform the composite analysis to look at the associated dynamical fields during the events or looking at the statistical behavior in terms of the precipitation extreme and so on. In our study, the wave phase 4 to 7 are termed at the west phase of equatorial wave, and the phases 1 to 3 and 8 are defined as the dry phase of the wave. We also calculate the changes in probability extreme rainfall and normalize it by the probability with respect to climatology. The extreme rainfall in our study is defined based on the 90th percentile of rainfall distributions. So the observed plateau we use are the graded upward rainfall data set from 1980 to 2007, and also localization data from BMKG from 87 to 2017. Keep in mind that we only focus over during the boreal winter from November to April, which is essentially the rainy season in Indonesia. So first, I want to discuss regarding the modulating impact of equatorial wave on rainfall extreme in Java, especially for Kelvin wave. The figure here shows the extreme probability associated with the wet phase of the Kelvin wave and the dry phase of the Kelvin wave. The hatching indicates 95% significant level based on a distribution independent bootstrap method on 1,000 subsamples. There are two key points I want to emphasize here. The first one is you can see here there is a coherent eastward propagation signals associated with extreme rainfall during the Kelvin wave period. So this signal first appear over the western part of the Java and propagating all the way through the east of the Java. And same case for the dry phase of the Kelvin wave. Second thing I would like to emphasize here is that the convectively active Kelvin wave increased the probability of extreme rainfall by up to 60%, while the dry phase suppressed the probability of extreme rainfall up to 52%. The same for the equatorial Rossby wave. So you can see here there is a coherent westward propagating modulation of extreme rainfall by the ER wave all the way from the east to the west. The equatorial Rossby wave increased the probability of extreme rainfall by up to 51% in upper right and 42% in the station, while the dry phase really decreased extreme probability rainfall up to 40% in upper right and 40% in stations. If you compare the modulating impact on extreme rainfall between the equatorial Rossby wave and Kelvin wave, it seems that the relation is much weaker compared to Kelvin wave. That is likely due to this weaker amplitude of equatorial Rossby wave for Java Island compared to Kelvin wave. So we also look at the mixed Rossby gravity wave, how it is influenced extreme rainfall. It turns out it has a similarity as the equatorial Rossby wave. It increased the precipitation extreme by up to 35% and decreased it by up to 30% during dry phases. However, compared to the other wave, it seems that the MRG wave are the least strongly coherent compared to the other wave. And this really makes sense since if you look at the amplitude of the MRG over zero region, it's much weaker compared to the other wave. Second thing that I look at in our study is the combined effect of the multiple equatorial wave on rainfall extremes. So our analysis show that the positive interferences of the equatorial wave lead to amplification of extreme rainfall probability. So as you can see here as the one in the color and the blue color shading. So interestingly, the superposition between this wave, especially when they are in phase, are approximately linear. For instance, if there is MGO in the wet phase occur at the same time where there is a wet phase of Kelvin wave, the relationship is really linear. It's really increase the extreme rainfall probability. However, the combined effect of different waves become non-linear when the two waves are in the dry phases. It's very important to note that the combined effect is a multiple of equatorial waves. It's really important since it really increased the chance of having rainfall extreme. One of the examples is the recent severe flooding that we had recently in 2020. So it seems like during this period, there is a combined impact between the MGO, the Kelvin, and ER wave. So using the data from BP and B, so we found that these three equatorial wave and type wave are contributing to the increasing of the local convection of the Jakarta. So in our other study, we look at the evidence that there are some flooding effects that are preceded by the Kelvin wave and some are not. So in total, there's only 30% of the severe flooding events in Jakarta that are preceded by the Kelvin wave, and the rest are preceded by low frequency variability and other local influence such as the cyclone and the Borneo vortex. The last thing that I will be discussing in this talk is that dynamics of extreme rainfall by the equatorial wave. In order to answer this question, so what we are doing is that we're using the moisture budget equation and we decompose the terms that is due to the vertically integrated moisture flux convergence and the term that is due to the vertical flux convergence that will be compensated by storage change. So essentially the positive VMVC means that you have a positive net precipitation, the increase in this value, which means increase the precipitations. So these figures show the composite anomalies of vertical integrated moisture flux convergence during different phases of the Kelvin wave. Keep in mind that the left-hand side show the wet phase of the Kelvin wave and the right-hand side show the dry phase of the Kelvin wave. First, we want to know that the increase in the VMVC anomalies occur in the region where the mass flux converge, consistent with the theoretical horizontal structure, which you can see on the right-hand side here. And this is pretty consistent with our analysis before. We show that there is an increased probability of extreme rainfall that is coincide with the increase the VMVC of this region during the wet phase, and decreased probability that is coincide with the VMVC divergence during the dry phase. So the vertical structure that we found here is also showed there is an increase of the specific humidity during this wet phase and during dry phase. The same conclusion we can also find from the Equator-Rossby wave that is consistent with the theoretical pattern that the convergent anomalies are collocated with cyclonic mass fluxes. It is providing condition that is favorable for increasing rainfall variability, extreme rainfall over Java Island. And during the dry phase, the region of negative moisture flux convergence is propagating westward and decrease the rainfall intensity, a result of the suppression of local convection. That's again consistent with the reducing of the extreme rainfall probability during the dry phase of Rossby wave. The last thing I want to emphasize here is that we also look at what control the VMVC by decompose this term into the convergent and affection terms. And we found out that the zonal convergent term from the Kelvin waves is the most dominant contributor for the VMVC value, while for the Equator-Rossby wave and MRG are mainly governed by the meridional convergence of the VMVC. But this term is mainly compensated by the zonal convergence. To summarize, so we found that there is a robust regional scale influence of equatorial wave on extreme rainfall over Java Island during the rainy seasons. Among these three types of wave, the Kelvin wave seems to be has the strongest influence over the Java Island, that increasing the extreme rainfall probability up to 60%. We also found that the positive equatorial wave interferences lead to amplification of the probability of extreme rainfall for Java Island, while the negative interferences suppress the extreme rainfall probability of Java Island. We also show the dynamics behind that, what control increasing of the VMVC of Java Island that is associated with increasing extreme probability rainfall for Java Island. So all in all, our results suggest that equatorial wave really important and provide important source for the predictability for extreme rainfall over Java Islands. If you want to know more about this study, you can check this out on our recent publication here. All right, thank you for your attention. That's it.
Thank you, Dr. Sandro. This is very interesting presentation, yeah. We will have a discussion session later on. So maybe now we want to invite our next speaker, Professor Scott Glenn. Are you there already? From the University of the State University of New Jersey. Yeah, please, Professor Scott Glenn, time is yours.
Thank you. There, can you see that now?
Yes, it's clear.
Perfect. I'm going to talk about some recent results from the North Atlantic hurricane glider picket lines that we've been doing in the United States for 3 years now. This will be our 4th year of working on this. I'm from Rutgers in New Jersey, but we have many, many partners in the US and throughout the world that are collaborating with us on tropical cyclones. This is some results from the US side of that collaboration. And the global tropical cyclone tracks are shown here. And so as you can see, it's a very big, it is a global problem. The World Meteorological Organization has kept statistics on this for the past 50 years, a couple thousand disasters due to the tropical cyclones where hundreds of thousands of people have died and over $1 trillion in damage as a result of this. So it's a very important thing to be studying. The other point about this is that for World Meteorological Day, one of the things the WMO is emphasizing the ocean and the importance of the ocean towards our climate and weather. And on the right here, in the right column, is an article by Lou Ussolini, the director of the Weather Service, who talks about the ocean and its importance to weather and the approach of an Earth system science to forecasting, where we are starting to include more of the coupling between the land and the ocean and the atmosphere to increase the accuracy of our forecast and the duration of our forecast. And so I'm going to show how we're doing that for the hurricanes in the US. And so the US has similar statistics. Oh, I'm having trouble moving this also. Okay, similar statistics in the US compared to the global. If we look at tropical cyclones here at the very top, the cost nearly $1 trillion in damage over the last 40 years due to the tropical cyclones. And if you compare that to all the other weather and climate disasters combined, tropical cyclones as a higher percentage of damage. So it's very important for us to be studying these and to provide warnings, to provide advanced forecasts so that people can get out of harm's way when they have to because of the severe amount of damage and deaths associated with them. And so if we look at our forecast statistics for the last 30 years, we have the official, the track errors on one side and the intensity errors on the other. And the track errors have been very impressive, how they've come down over the years. We're getting very good at forecasting track. And a lot of that is because our regional models are embedded in a very good global model, global ensemble. And we can get those steering currents and we have a very good idea where those storms are going to go. But the improvements in intensity have lagged. And we don't always know what that intensity is going to be at landfall. And that's a very important piece of the information for the evacuate or shelter in place decisions that are often made several days in advance. You may know a hurricane is heading towards you, so you're going to get hit. But is it going to come in as a tropical storm or a Cat 5 hurricane? Makes a big difference of whether you shelter in place or evacuate. And so one of the things that we wanted to look at more closely was the ocean, because the ocean is the energy source for the hurricanes and it has an impact on the intensity, among other things. So let's start to look more closely at the impact of the ocean heat as this energy source. And we began this process by looking at the tropical cyclone heat potential. And here's a map of that heat potential over the North Atlantic hurricane regions. You see the tracks of the hurricanes as they're heading towards the coast. And you see the dots showing where hurricanes intensify, where they change from one category to another. And you see a lot of those dots are well correlated with the color contours of the ocean heat content. And so where there's more heat, there's more of these intensification events. But statistically, that may be what's going on. But if you start looking at the details and try to look at the dynamics of how this ocean is coupling, you see that it's much more complicated. And we found that it's not universal. One of the areas that I work in here up around New Jersey, where there's very little ocean heat content at all, we found 3 classes of hurricanes that come in this region. And all 3 of those classes depend on how the ocean is going to respond to that. And sometimes those hurricanes cause the ocean downwelling in the ocean, which will intensify the storm. Some will cause upwelling in the ocean, which will weaken the storm. And some will cause mixing of that ocean water, which will weaken it. And so these intensity modifications are due to that rapid coevolution of the ocean and atmosphere in this region in New Jersey. Similar at the other end, at the beginning of this track of hurricanes through there, with my colleague Gustavo Goni at AOML, where he's working there. He sees that the Amazon and Orinoco rivers, the barrier layers of fresh water that come into the area, have a big impact on inhibiting the mixing, keeping the water warm, and rapidly intensifying the hurricanes. So we see that there's many more processes going on and many more features that we have to track than just the ocean heat content. So that makes it a little more complicated. And when we go around to our colleagues around the US, we find that the essential ocean features that are impacting hurricane intensity, they vary regionally. In my area around New Jersey, there's this seasonal stratification in this cold pool. And that cold pool at the bottom, whether it's upwelled or downwelled or mixed, totally controls how that hurricane is then going to weaken or intensify as it's coming towards the coast. On the southern side of this area here, we have this heat and this freshwater inflow through the passages in these windward islands of the Caribbean. So that conveyor belt, the global conveyor belt, as it advects that fresh water in through there, has a big impact. And then we have, of course, the loop current through the Gulf of Mexico and the Gulf Stream, which are carrying warm water with it. And with those ocean features in the areas there, we started looking at where do we need the ocean data the most. And if it's those last 3 days, we're trying to increase our storm surge forecast from 2 days to 3 days. And that's colored in red here. So it's right as these hurricane tracks are turning from gray to red and coming into the coast. And the sampling systems that we've chosen for that are the gliders, of course. They're shown down here in yellow. And our concept of operations, how do we operate these things? We have hurricane hunters. Those are the airplanes for rapid response. They dress in white like a soccer game and they fly through the air and they chase the ball. We are like the goalie in a soccer game. We patrol the land, the water just offshore, and stand there and wait for the hurricanes to come so that we can make sure the ocean is on track. I have to move this again. There. And so how did we do this last hurricane season? We see here's our 2020 statistics from the glider operations. 16 institutions on the lower right all collaborated, coordinated their glider flights to make sure that we had the different features identified with the gliders and assimilated into the ocean models. 78 glider missions total along the coast. You see them all colored in here by who was the main sponsor. Over 3,000 glider days, 163,000 additional data profiles were provided to the global telecommunication system so they could be assimilated by the model. This is an order of magnitude. This is 15 times more data that's normally available. And as you can see in the 2018 and 2019, we've increased the data that's available. We had glider data in 15 storms. As a result, I'm going to show the example from just one storm, one forecast, but it's a wonderful year of science storms for us to look at. Here's probably the most famous forecast cycle of the entire season. It was Hurricane Laura as it was over Cuba and forecast to come into the coast here around Texas, Louisiana area. And as the landfall, it was a very highly accurate, in green here, forecast for where it was going to come to shore. It was remarkably accurate within 1 mile of where a landfall was actually going to take place 3.5 days in advance. So that's a wonderful testament to how good the global models are becoming. But let's look at the intensity of the forecasts over here. Black is the actual best track, the intensity of the hurricane, and red was the forecast that was put out. If we look at the spread in the models that was occurring there, there's a 90-knot difference between the lowest model, which never left tropical storm, and the highest model, which increased to Cat 5. And so they knew they were going to get hit by a hurricane, but they didn't know it'd be a tropical storm or a Cat 5. So what do you do? That was the big question that was before us. And one of the bright spots of this whole activity was we found that one of our best models, the H-Wharf model in purple, it was coupled to a new data simulative ocean model that assimilated all that data for the very first time. And it was coupled on August 5th. And it's this purple line. And it was able to get that rapid intensification, that very hard to capture rapid intensification 3.5 days in advance. So this is one of the most important cases that we'll be studying now, as to what was so special about this case when we had the best ocean with the best atmosphere combined. Why was it able to do this forecast and the other models weren't? So how are we expanding from there? We're looking at coordination across sampling platforms in the US. Here's the Argo floats that were in the area and the gliders that are near shore. We're also looking at surface drifters, how they come in through the Caribbean and go through and coordinate with those, and also the sail drones that can go across the surface and get the atmospheric measurements too. We're working with Australia and their glider fleets that they put in both tropical storms and extratropical, so we can expand the type of storms that we look at. We're working with groups in Korea where the typhoons are really strong, and we can put the gliders out there and we see the rapid intensification or weakening.
Sorry, Prof, about 1 minute, yeah.
Perfect, perfect. And then in the Caribbean, where we have the gliders flying along those passages. And so just like through Indonesia, all the flow through the passages, we want to be able to monitor the flow through the passages there. And so our last slide, the ocean gliders is our network, our global network that we're building through this for the global ocean observing system. We have several working groups that are in there. One of them is the global storm forecasting working group. If people are interested in these technologies and working them in storms, our next steps are shown along the bottom to enable any glider deployed at sea to contribute to these improved forecasts. That's what we do with our glider data management, making it easy for you to contribute to improving those forecasts. We want to develop a global capacity to operate these gliders in storms everywhere. And so that's part of what we do as a group. And then we're trying to add more and more sensors. The tropical sensors really benefit from the simple temperature and salinity sensors, but as we go into more and more other types of storms, other sensors are going to help us too, physical and biological. So thank you for your time. I appreciate your attention.
Yep, thank you, Professor Scott. So from the previous two speakers, just in 30 minutes, where you learn a lot about the tropical dynamics. Yeah, we learn about extreme, and then now we learn about heat potential. The third one, I want to invite Professor Courtney Schumacher. It's Schumacher, right? Not Schumacher, right, Prof?
Schumacher, yeah, Schumacher. You were right
Schumacher.
the first time.
Okay, it's your time, please.
Great, thank you. I would first like to thank the conveners for inviting me. This is really a pleasure to be speaking at this event. I just wish it was in person. So I will be talking about rainfall over Sumatra, especially the topographic influences at multiple time scales, a variety. And then I would like to definitely recognize my graduate student, Hidanshu Bai, who did a lot of this work, and I have other collaborators at Texas A&M, but most importantly, I'd like to thank all of my collaborators at BMKG, who have been a pleasure to work with, and I look forward to future collaborations with them and others at BMKG. So I'm going to start out looking at just a very basic annual map of rainfall. This is very consistent with other satellite climatologies, but the nice thing about this is that it's with a very high resolution data set from the TRIM GPM satellite called iMerge. It's a 0.1 degree or about 10 kilometer data set from 2007 to 2019. And that high resolution lets us isolate orographic patterns better. And just to point out, again, this is not a new result, that offshore, which is just west of the mountains here, can people see my cursor? Yes? I don't know, pretend that you can see my mouse.
I cannot.
Is that, yes, good.
Now I can see.
Okay, good. There might be a delay. You really have your strongest rainfall right offshore within about 150 kilometers of the coast. And this is up to 12 millimeters or more per day. And then over the mountains, we do have enhanced rainfall, but not as much as off the shore, on the order of 8 millimeters per day. And we have the least rainfall to the east of the mountains on the order of 6 to 7 millimeters per day. And I'd like to point out on all the maps I show, that I'm going to outline the 500-meter elevation here, just to know that, to understand where that really, if I go back, this very intense topography along Sumatra is very steep and along the western coast. Okay, so my first question is maybe, what is the type of rainfall that occurs to cause these patterns, or are they related to convective organization in any way? And when I talk about convective organization, I often separate the rain into convective rainfall, which is from these deep and intense towers, and versus the stratiform rainfall, which falls from large, weaker precipitating anvil, but it covers large regions, and so it can add up to a significant amount of heat and moisture transports. So when I say organization, I mean how much of the rain from a system is stratiform, and typically if there's more stratiform rain, it's a bigger and long-lasting system. So I'm still in my annual time scale, and this is the only time I'll be showing data from the TRIM and GPM radar rather than the iMerge data set, which is from a passive microwave collection. And then this is slightly coarser resolution, but here you can see the stratiform rain fraction off, if I can go ahead, offshore is moderate on the order of 45%, which is actually pretty good near land. And then we get, which suggests reasonable convective organization. We kind of get higher, even higher values of stratiform rain fraction over the mountains themselves, which is surprising and maybe a false signal because of the satellite retrieval. So I won't go into that in any more detail. But over the east of the mountains, it's a signal I trust. We have lower stratiform rain fractions, more about a third of the rainfall from stratiform rain. So it's less organized to the east of the mountains. And I'm not going to show it, but I would like to say this sort of west-east pattern is very similar during the passage of the MJO. So there's something fundamental about this setup of Sumatra and its topography that affects convective organization. So there might be many things that impact this, but one we looked at was moisture. Convective organization happens in highly moist environments. And we postulate that the moisture gradient on the east side of the orography over here, which is in the negative values over on this map, I'm taking a cross section at 2 degrees, which is what this map is showing here from ERA 5. And we see there's positive values on the west side of the mountain where we have more convective organization, and then negative values on the east side where that suggests that moisture and its pattern is making it harder for convection to organize or even to stay organized as the MJO envelope crosses over the topography. So now I'm going to jump to my next time scale. So speaking of the MJO, so I'm indicating annual to MJO. So now I'm showing the iMerge rainfall for the active and inactive periods of the MJO. It doesn't really matter how I define it. I think we all know that there's more rainfall as the active MJO is present. But then I wanted to point out that this really strong east-west difference in rainfall exists both during the active and inactive period. So we have a lot more rainfall to the west of the orography and a lot less to the east. And so which is very similar to the annual map. And so then if I just focus on the MJO only, if we did a harmonic analysis, again, I'm back to the iMerge. This is on the iMerge daily rainfall. And this just show that to the west of the mountains, the MJO really does impact the rainfall quite a bit, but to the east, it does not. So it's sort of like the east of the topography doesn't care that the MJO is passing over. And so then now I'm going to say, well, I guess what is it about the west side of the mountains that's so interesting? Where does a lot of that rain come from? And I think, again, we know that from I'm jumping to my next time scale, to the diurnal time scale. I'm back, and these are I-merge rainfall anomalies now. So during the day, actually most of the rainfall over Sumatra is happening near the peaks of the mountains, and maybe a little bit on the far east coast. But it's really at night that we're getting the strong rainfall, the enhanced rainfall to the west, and actually to the east as well, but not as strongly, and I'm not going to focus on that as much. And so this is sort of the place where I'm going to really focus on this enhanced nighttime rainfall and how that relates to the MJO. So now I get to jump to the work I did with that we did with the Indonesian group. The Indonesia has an amazing radar network, and we chose just one of the radars, the Padang radar. We had a year of data, about 280 fully good days of data during 2018. It's very high resolution, both in space and time, that we can really look at the idea of what's happening offshore in terms of rainfall. Oh, and I should point out, this paper has recently been published in the Monthly Weather Review, and I'm only going to go over small parts of it in this talk, but I would recommend going to look at this paper, or I would be happy to provide it to anyone who would like it. So now, because first we know that from past literature that there's propagating systems that often happen off the coast of the maritime continent islands. So we flip the Padang map, and we only look at the western half of the radar domain and the Havmalers in that domain. And so if I give you an example of rainfall Havmalers during February 2018, this is these are by day here, you're going up in time. And you can see that we chose nocturnal rainfall events based on very clear rainfall propagation that starts in the later afternoon or early evening hours. And then, so it doesn't occur every day. We have rainfall that occurs only some of the time in terms of the offshore propagation. And if you actually look at the whole year, we had 117 nocturnal offshore rainfall events, about 40% of the days we had. And that the mean propagation speed here, you can see, was 4.5 meters per second. And then this is something you can see, this is a non-propagating signal from Seabird Island offshore. So this is sort of a daytime signal that's not propagating. You can compare that. This signal is really important because the speed indicates that it probably isn't a gravity wave. This is too slow for a gravity wave. So near the coast, we postulate in this paper that this has to be associated with a land breeze. And so what this means is that you have a land breeze at night coming offshore, and that the onshore or the onshore flow from synoptic flow from monsoons or other synoptic flows will converge with the land breeze, cause convection that then propagates offshore during the nighttime hours and dissipates when you have onshore flow. And so that makes sense. But when we actually looked at when we actually looked at the surface data from the BMKG observations at the Padang airport, we noticed that if I'm going to flip back and forth, the land breeze is actually a lot weaker than that picture suggests. And so we have very strong onshore flow during the day and weak offshore flow at night. And so if you look at the events that this is the ERA 5 large scale winds for 2018 for when we had offshore events versus no events. And you can see that we did have onshore flow, but it was kind of weak. And when we had no events, the onshore flow was quite strong. So instead of providing extra convergence, it overwhelmed the land breeze. And so now I'm flipping, now we can think of, well, now I need to link this back to the MJO because I had been talking about that before. And does the same thing happen during the MJO? Well, yes, it does. And in fact, this was an interesting result to us. This is the MJO winds during phases 2 and 3. So as the MJO is approaching the maritime continent, versus phases 4 and 5 when it's over the maritime continent. And if I flip back, you can see that it looks a lot like, as the MJO is approaching, it looks a lot like the flow when we actually had nocturnal events, and that's true. So most of our nocturnal offshore events happened when the MJO was approaching rather than when it was over the maritime continent because of the strong low-level winds. So here I've pointed out moisture is really important to rainfall on either side of the mountains. as is the wind, the large scale wind flow, especially how things like the annual mean, the diurnal and the intraseasonal rainfall variations exist and how they interact. I think this is my last slide before my conclusions. And this is to kind of bring it all together in terms of what does this mean for the diurnal and MJO interactions over Sumatra. And the nice thing about this satellite data is that it can help us kind of hone in on the regions that are most interesting. And then I would love to do for future work on with other radar data sets from BMKG, with collaborators and other islands to see how these patterns play out with different orographic configurations and different impacts of large scale flow. So this is a k-means clustering, again, using the iMerge data. And so the cluster here, 1, means, and this is in relation, this is the diurnal cycle in relation to the MJO. So if you're in cluster 1, this means you're here. So this means you have your evening peak before the MJO peak. So the MJO is the black line, and the evening peak here is the blue line. And so this is our offshore propagation signal. So we know the clustering is doing really well compared to the Padang data I just showed you. The cluster 2 is when we have our afternoon peaking before the MJO envelope. And this makes sense before it gets cloudy. There's a lot of daytime heating and the land can really heat up, especially over topography. And then the thing I really wanted to point out here, especially, was 2 and 3. So to the east, we're really in a different regime than west of the mountains and over the topography. We're starting to get really into a regime where both the afternoon and evening peak with the MJO, and then you have really the morning peak happens much further in front of the MJO on this side of the mountains. And so this is again suggesting the diurnal timing. I actually took this picture. I'm really almost done. I took this picture from, and I'm sorry I don't have the reference listed. It's not my schematic, but the idea of, yes, there's offshore propagation and then over water, and then you have mountain winds that impact the onshore propagation, for example, to the east of the topography. But the timing, you don't always have the same westerly winds and the same moisture. If you vary the westerly winds, their magnitude, even the direction, and the moisture, you're going to change the timing and magnitude of these diurnal patterns. And so that's sort of the point of this figure. Okay, so I think I'll just leave out my summaries because I'm exactly at the time, so we don't get delayed. But I can leave these up for a minute.
Thank you.
I should maybe, as people are reading through them, the one other thing, we did look at seasonal changes as well. And so the flow changes that you get with the MJO, we also see very similar changes in rainfall patterns and the offshore propagation with the seasonal changes in monsoon winds and moisture. So that's just, I didn't have time to show that.
Okay, it's up.
I need to stop sharing.
Yep. Thank you very much, Dr. Schumacher. So I always remember the speed drivers. Michael Schumacher.
Yes, Michael, we're not related.
Thank you. It's very interesting after hearing about the ocean, and then we hear from you about the land influence on rainfall. This is excellent. Yes. And then the next speaker, I want to invite Dr. Seong Yoo Hong from NOAA affiliate. Dr. Seong Yoo Hong, are you ready? Okay, time is yours. Sorry if I misspell your name, yeah, Dr. Seong Yoo Hong. Time is yours, Doctor, please.
Okay. Where is it? Do you know how to?
Can you do the share screen?
Yeah, share screen. I don't know how to do it.
Just click the green button below.
Wait a second.
Share screen.
Green button, yeah.
There is a share screen down below, and then just click it
right.
and go to your presentation slide.
how come I don't see my preset file? Let's see.
Yeah.
I have a file of my Dropbox. Sorry.
It's okay.
Share. And then
Yeah, just
standard,
click.
right?
Yep. Just click share
Desktop.
screen and then go.
But I don't see my, okay.
Just
Okay.
click the share screen, go to your presentation slide. It will pop up on the
Yeah.
Zoom.
Yep. Terrible.
We can see you now.
Okay.
Yes.
Okay. Great.
Yep.
Yeah. Thank you very much. Okay. This is Seong Yoo Hong. I started to work on the NOAA ESRL since last week, only 1 week. So I'm going to talk about the new model development in Korea for 2014 to 2019. Before doing that, I was a professor of Yonsei University, Seoul. Okay. Yeah. The purpose of the KIAPS organization is to develop a Korean-owned global focused model. It is a 9-year project, about $10 million per year. There is about 60 regular employees and about 40 scientists. And next, no. Please next, yeah. Time schedule is 3 stages. First 3 years of basic research. Stage 2 is to develop KIAP's own research-based semi-operational model. Stage 3 is the final operational system. I served the director from the start of 2014 to 2019. For 3 years before I joined the KIAPS, there is standard activity, adopt the existing model, for example, thermal core from the NCAP climate model, and then plug it in the physics packages from WRF for Green's GFS model. There are also activities of premature data simulation of a physical grid, but there's no result over the NWP, and that there is a simulated climatology result. So September 2014, I started a strategy developing KMA own model. That means the reference model. When you develop Tanko core, we refer the other model Tanko core. While developing Tanko core, we revised the physics package using the established model, for example, WRF model. So that develop major component of a model, but the strategy of benchmarking performance of KIM with the reference model. In other words, KIM was coded from the scratch with major scientific elements except from the previous development to publication. The name of the model is acronym KIM, Korean Integration Model. Yeah, next. And that, for example, Tanko core is a non-hydrostatic over-cubital sphere, also spectral element, fully compressible. So we designed carbon equation and then developed the 2D shallow water test for various DCMAP tests, and then extended the Tanko core test, also attended the DCMAP intercomparison. And they extended 3D model, time drive model, and then coupled the full physics packages, and eventually 3D atoms model, or eventually coupled the data simulation system. According to Joe Clamp, that this is the first fully functional analysis spectral element core. Okay, next, thanks. For physics, mostly adapted from the existing modules. For example, this is the Cumulus parameter scheme. Left is an observation of a red column is 300 millimeter per day. And then version 1.0 adapted from the NCGFS didn't reproduce heavy precipitation. It is a amount of precipitation over a central part of a peninsula less than 40 millimeter. We improved the triggering function of the SAS scheme and then recovered the 300 millimeter over the region where it was observed. Next. And then this is a physics package improvement between 2 years. YSU 2013 is the Grimm's model packages, and the KIAF 2015 is the 2-year activity. So that while Tango Core and the Ossimile being developed, this model had been improved in WRF or GRIF platforms. Next. And data assimilation, we had to build it from the scratch because there is no data assimilation system over this cubic sphere grid. So that we designed the cubic sphere grid 3D bar and then assimilate the data from radar data and then aircraft and cell data one by one. Next. And data processing, it is a long-term for 9 years. Conventional observation and cell data from the research and the development, implementation, and the operational. Okay, Kim physics package, you can see that's 3.1, mostly rooted from the existing model, where I led the development of the physics model, for example, YSPBL or the WSM5. But there is some new module we have to develop, for example, radiation scheme. Also, gravitational scheme is totally newly developed. So that exactly, okay, good, next. Exactly 4.5 years passed, which is half of the 9-year project to build the full NW system. So that is 2015 July, we built the real-time focus system, and then 2017, we merged the 3D bar LHKF for the ensemble bar, and then higher resolution. And then 2018, we published the Kim paper, and then parallel studies to 18. 2019, semi-operation started, and then April 2020 is operational. So performance. Next. This is the performance of Kim 0.4 late 2019. RMS error of 850 millibar temperature. So that is focus time 1 to 6. So that smaller is better. 2 versions of Kim is outperforms to any of the model. Kim next better good performance is the JMA model, and then Medoffice model and was GFS model. Okay, next. This is the example of real semi-open forecast. This is a Typhoon Hagibis. Kim is the very solid for different initial time, so that there's very little spread. GDOPS, which is the KMA United model from the UK Office model, some widespread for the only longer extended focus. There's a widespread in the when you approach the Korean Peninsula. European Center is good, but it's Kim is robust for this case. Yeah, next. This is the example of the Kim and UM model, United model. So that shady is precipitation, solid line is sea level pressure. You can see that very similar up to 5 days. Yeah, for typhoon is approaching. So focus to satisfy the performance of Kim against UM model, so that they decide to go with Kim for operational. Okay. Yeah, okay. Then the skill evaluation of the skill score needs to be continuously improved. Subject focus skill from KMA focus is competitive to that of KMA UM. Okay, next. And this is a evolution of a skill for 2015 to by the time of KMA, KIAPS closed, about 98%. 90% of global measure of 500 millibar anomaly coefficient. Two major upgrades before closing QS, but I don't have access to the performance since that time. Next. Yeah. We also attended the intercompany project, for example, dynamic preparation. You can see that all other model IFS UM had an earlier peak, also exaggerate magnitude. Kim is a solid line, very well follow the observation. Okay, next, yeah. And then this is also attended the gravity direct intercom project. Is that we can identify the improvement room by participating in intercom project. Next, please. This post KIAPS started December 2020. There is about 1 year gap between the KIAPS and post KIAPS. There is some issue for the from the Congress. So post KIAPS generally unified model from short range to extended forecast, sub-seasonal forecast, covering regional to global model. Yeah, next. This is my subjective point of view for future Earth modeling. So left panel is the typical activity, standard activity for the modeling center is pursue. All the coupling is the aerospace and the water atmosphere. Go to the over 600 kilometers.
1 minute, yeah, Dr. Hong.
Okay, thank you very much. I think, please, previous one. Yeah, I think the current activity, what model is doing is only half. We need to include that human active model. Okay, yeah. Yeah, this is concluding remarks. I already did, yeah. Thank you. This is the end of my talk.
Thank you very much, Dr. Hong. So now we learn a new way again about the modeling side, how to improve our modeling skill, based on the theory that we learned before. For not further ado, I want to invite the next speaker. This is also from NOAA, Dr. Chidong Zhang. Dr. Chidong Zhang, are you there?
Yes, thank you. Can you hear me?
Okay. Yes.
Okay, let me try to
hear you clearly.
Share the screen.
Yep.
I'm not able to share the screen.
Please, the organizer, can you help? Allow Dr. Zhang to share the screen.
I click the share, nothing happens.
It just worked well on my side. Can you click the share screen button, the green button down there?
Yeah.
Yep.
Okay, thank you. All right, so thank you for this opportunity to give a presentation at this conference. I'm going to talk about a concept called the coastal transition zones. I'm not an expert on coastal research, but this is something that I have been thinking about lately, and I would like to take this opportunity to share with you some of my thoughts and hopefully can stimulate some discussion. The whole idea is to treat the coastal zone, including the ocean, the land, and atmosphere as a single identity. So the concept of coast transition zone is now new. For example, in this slide shows that on the left, that underneath the ground, underneath the surface, the groundwater beneath the ocean is salty, and the groundwater underneath the land surface is fresh. And when these two types of water meet, there is a fresh to salt water transition zone. That's underneath the surface. And in the ocean, there's also a coastal transition zone that is from deep ocean to continental slope, then to continental shelf. So the depth of the ocean gradually changes. And that is another type of transition zone. Next, please. Next slide, please. All right, but what I'm going to talk about is the transition zone actually between the atmosphere, the ocean, and the land. So let's just look at the water. We know that in the water, the Aeros interaction happens. The Aeros interaction happens from the air-sea interface, that's the sea surface, going down to the upper ocean, where there's many structures, such as mixing, such as upwelling, wave activity, and so on and so forth. Then above the surface, in the atmospheric boundary layer, there's also many activities, different type of cloud, and the turbulence, and the different vertical profile. So the Aeros interaction really does not only happen at the sea surface, it happens from the upper ocean through the air-sea interface to the atmosphere boundary layer. The entire zone is the continuous air-sea transition zone. Next. The same concept applied to overland. Overland, you have a soil. Above the soil, you have vegetation. Then above the vegetation, you have atmosphere boundary layer. And underneath the surface, you have groundwater. And at the surface, in addition to soil and vegetation, you have all different kind of water, river and lake and so on and so forth. So the land-air interaction does not only happen at the land surface, and land surface actually is very difficult to define. It actually is from the groundwater to the surface features to atmosphere boundary layers. Again, this is a transition zone that need to be considered as a whole. Next one, please. And if you take these two, air-sea transition zone and land-sea transition zone, and put into the coastal region, that will become even more complicated. As we discussed, that in the water, you have from deep ocean to shallow ocean, and then land, you have different land features, and on top of that, you have atmosphere boundary layer that connect the land and ocean. So this is really a three-dimensional, three-component interaction. And how to treat that is a critical element to study the coastal zone. Next, please. So the reason I want to bring this up to this conference is if we look at the maritime continent area, this coastal transition zone is more important than anywhere else on Earth. Because if you look at the maritime continent, there's no place you can find that's purely continental or purely land, or no place you can find is purely ocean. Everywhere you go, you have to consider the land air interaction, the ocean air interaction, and land and ocean interaction. So this is a place that truly the three components has to be integrated together. And one typical example is the diurnal cycle. We have the land sea breezes. We have the convection propagating from land to ocean. You hear Professor Schumacher talk about this. And then the coastal zone has a very complicated mixing, tidal, tide, current, upwelling, and convection, advection, and so on and so forth. So it's all integrated air, sea, land interaction. Next, please. All right, so there's a missing figure, but that's okay. So in terms of Yeah, next one, that's fine. In terms of observations, BMKG and other government agencies in this area has established a wonderful observing network over land in terms of soundings, atmospheric soundings, in terms of surface meteorology stations, rain gauge, and radar networks. It's wonderful. But you look at over water, that could be a different story. Next, please. So this is a recent distribution. I think it's last month, February, yes, February 2020, last year. Distribution of ocean observations, and each dot represent one platform. And you can see in the global ocean, it has pretty good coverage, except in the Arctic and maybe near the Antarctic. However, if you look at the maritime continent ocean, there's a big gap there. So that's somewhere we have to fill. And to fill that gap is not easy, but we have technology that can help us. Next, please. So these slides summarize the current technologies that we can use. Some of the traditional, like soundings and ship observations. Some are pretty buoys, for example. Those are conventional, traditional observation platform. Then we have some modern platform. You heard Professor Scott talk about gliders, and there's different kind of floats, and there's different kind of surface vehicles such as wave gliders and sail drones. Then we have the uncrewed aero vehicles that you can use. Of course, aircraft drop zones and aircraft measurement has always been there. So the question is how we can take advantage of those conventional observation technology and the new observing technology, put them together and design a ocean observations that is not only for the sake of ocean, but for the sake of ocean, air, and land interaction as a whole. In other words, how do we combine the ocean observations with the land observations and atmosphere observations and put them together? Next one. So this is my last slide. So basically, I just want to share the thoughts that in the maritime continent, we have a great opportunity to build a network of observations, not for only or land or atmosphere only, but for the three altogether. And this is a great challenge. And I think with a careful thought and enough support, I think we can do that. We can make the maritime continent a great example of establishing a land-air sea interaction or coastal transition zone observing network. So that's my my key point. That's it. Thank you very much.
Thank you very much, Dr. Zhang. So you explain about the important to further understand about the Earth climate system, yeah, not only and put together about the land, atmosphere, and ocean. So I'm very happy. We are now still 8:56, and we already heard from the speaker who are from the US mainly. As I graduated also from the US, it look like I go back again to the campus to listen to all of you guys. So now I want to invite the next speaker. It's a bit different now from Jamstack, Dr. Muteki Kosaku. Yeah. Hopefully I don't misspell your name, Dr. Muteki. Time is yours.
Yes, thank you, Chairman. Can you hear me?
Yep, I can hear you clearly.
Okay.
Your beautiful picture.
Thanks. I'm gonna start. So good morning. My name is Muteki Kosaku from Jamstack. Today, I'd like to introduce the most recent YMC observation called CSO. CSO means cold surge observation that was conducted during the period of 8 January to 8 March in 2021. It was just finished 3 weeks ago. This CSO project is a part of YMC and conducted under the collaboration between BMKG and JAMSEC. During the YMC CSO, we have fortunately observed 7 core search events. I want to share their features from now. And maybe you know, cold surge sometimes crosses over the equator. That is especially called as cross equatorial northerly winds, that is called SENS. So I'd like to talking about SENS from now. And first, before starting this report on the project, we'd like to express our sincere gratitude to all BMKG staff for their best operation, even under the strict restrictions of COVID-19. And the objective is to detect this modification processes of the air mass at the head of cold surge and the convection development and the severe weather, including torrential rainfall, by the intensive aerial observation at Jakarta and the Pangkal Pinang, vapor variation observation with GNSS network in Indonesia, and the precipitation radar network. So first of all, what is cold surge? Maybe you know, cold surge is the cold air outbreak near the surface from the cold high pressure over Eurasian continent. And especially, the cold surge sometimes crosses over the equator like this. So we call it cross equatorial northerly surge SENS. So we want to focus on it. And specification of the CSO project is like this. This is very, very simple project, intensive radio sound observations of 4 times per day for 60 days at 2 locations, Pangkal Pinang and Jakarta Airport, International Airport. And also, in addition, 600-gram balloon radio sounds once per day at 06 UTC to get higher than 30 kilometers at Jakarta. So here I show you a map of operational upper sounding network in the circumstance of the path of cold surge. At the Aeros points, BMKG staff did upper sounding operation 4 times per day using Meisei IMS 100 sensor provided by JAMSTEC for additional 2 times at 06 UTC and 18 UTC. And also, we have the additional GNSS station at Jakarta to obtain hourly PWV, precipitated water vapor. This is an example of the time series from the beginning of a IOP for 3 days. Maybe you can see that PWV peak of 63 millimeter. That was a few hours prior to rainfall peak, intense rainfall peak of more than 30 millimeter per hour, and also we have a significant temperature degree decrease, more than 5 degrees Celsius, like this. And before going to the overview of weather condition during this year, so I want to share you the way to communicate with BMKG and GEMSTEC staff remotely under the strict restriction of COVID-19. We established virtual observation field through WhatsApp group chat like this. And we were always talking about everything on this project every day. And so, for example, transportation and administration procedures, the way of equipment installation, friendly daily communication, and the operation report, everything on it established over the WhatsApp group chat. That was actually 100 times faster than email communications, though it is better to working together in real space, of course. Anyway, we can find this kind of communication is very, very useful to candidate to conduct observation project. So let's move on to the overview of IOP. The entire IOP was very dominant by northerly winds over Java Sea. This is the time series. This is the time series. Of 0.55 meridian wind speed average for this box. And there were 7 sense events like this, according to Hattori et al. 2011's paper criteria. In addition, the first strong cold surge here before 1 week before sense 1, and it also have associated with the strong rainfall over Jakarta. And based on that, this is the time latitude cross-section of GS map rainfall by color, like this, and surface wind vectors over there. So the continuous rainfall over the Java Islands, like over there, here, at the head of cross equatorial northern winds here. Also, please focus on their sense 6. We have their sense 6 induced the extreme rainfall over Jakarta. That was over 150 millimeter per day in the western part of Jakarta. That was very severe flooding, and more than 8,500 damaged houses across West Java province due to the overflow of river were reported. And next figure shows the NOAA's or SSD anomaly by color and SSD contents. The negative SSD anomaly less than -1 degree Celsius continued over the South China Sea here. That is very, very significant. And over the Java Sea around here, we have the negative SSD anomaly of -1 degree to -0.5 degree Celsius. Continued for the period from the 16th January to 26 or the end of February, almost. So all of seven sense event occurred in association with these negative SSE anomalies over the Java Sea. And from now, I'm going to show you a time height cross section from CGK, PGK sounding profiles that is during the IOP. This is for CGK, Jakarta Soekarno-Hatta International Airport. And you can see that sense 1 has a negative U anomaly, and all the others, sense 2, 3, 4, 5, 6, 7 have their positive U anomaly here in association with MJO enhancement over the Western Pacific. And this is for CGK, no, this is for PGK. And also sense 1 has the negative U anomaly too, and the others have the positive U anomalies in association with MJO enhancement. Next one, it will be a meridional wind speed anomaly. Looking at the meridional anomaly, you can see that all sense 1 to 7 have the negative B anomaly. Anomalies in the lower layer less than 5, at least 5 kilometers. Especially sense 6 here, sense 6, including inducing severe flood in West Jakarta, has the most significant negative B anomaly near the surface. The next one is for PGK. Such features are almost the same at PGK. However, notable point should be the fact that sense 2 to 7, sense 2, 3, 4, during the MJO phase of 6 and 7, located in Western Pacific, have the deeper layer of the negative B anomaly here. Actually, the MJO signal was very weak for the phases of 4 and 5 over the maritime continent for just beginning of IOP during January here. But MJO signal became much significant over the Western Pacific here during February. So the combination of MJO and the cold surge or some interaction will be interesting issues for the future. And also here we have averaged mapped for each sense event like this. This is for sense 1. All sense events have a large scale pressure ridge in the meridional direction and the large scale northerly flow like this. Penetrated over the East China Sea, South China Sea, and Java and inland seas of Indonesia, like this. All of sense events have such features, and also we have the MJO convection over the Western Pacific just as for the sense 5 and 6, like this, we have twin cyclones here, and also sense 6 is inducing torrential rainfall and severe flooding over Jakarta behind the MJO, and it is associated with the very, very strong northerly flow, like this. And also we want to introduce the SST maps, like this. We have the looking at the SST anomaly field, you can see the significant cold tongue distribution over the South China Sea, like this. Also, it is strengthened during the IOP, and finally, let's move on to summary. Remote collaboration by group chat worked very well under strict restriction due to COVID-19, and fortunately we can observe 7 sense events during IOP, much more frequent than usual, and also sense 6 during 18 to 21st February induced severe flooding in West Jakarta. The significant negative SST anomaly were continued over the inland marginal seas of Indonesia under the strong northerly surge condition. Thank you. That's all.
Thank you very much, Dr. Moteki. It's interesting research, yeah. Again, how we observe our ocean to understand about the cold surge. So in the tropic. So this is very interesting. So now we are 9:14. Thank you for 1 minute. I look at the time for the next speaker. I want to call Dr. Mori Suichi.
Yep.
Again from Jamstek. You are there already?
Can you hear me?
Time is yours.
Okay.
Yes, very clear. Sensei Mori.
Yep. So hello everyone. My name is Shuichi Mori, Jamstek. So today I want to talk about the little older two campaigns, pre-YMC 2015 and YMC Sumatra 2017, rather than Moteki's previous talk. Of course, this project was done by international collaboration among BMKG, PPPT, and Jamstek. So I suppose most of you already well know about these two campaigns. The southwestern coast of Sumatra was the target area, and we deployed our research vessel Mirai off the coast of Sumatra for about 1 month long in each campaign period. And also we made a very good land observation site at BMKG, Benkuru station, and nearby another some observation site. So in the two field campaigns, we have very good data, and most of the interesting features have been published by Yokoi et al., Monthly Weather Review, 2 papers, and also recently Gen et al. Published their paper. They introduce some differences between two campaigns, the amplitude of diurnal convective system and phase speed of coastal migration. That is very similar result with the previous talk by Professor Courtney Schumacher. And now I would like to focus on the lightnings. Lightnings were also observed over the coastal land before the MJO onset, in particular in year 2015. Every day. But completely no lightnings after the MJO onset, with strong westerlies in the lower troposphere. In addition, almost no lightnings were observed in the 17th campaign, even in MJO inactive phase. So this time we'd like to introduce some results based on the radar and sounding data. Before that, I'd like to show you the radar coverage for our 2 campaigns period. The blue circle shows the largest one by the observational range of the BMKG C-band Doppler radar, and the red one shows the Mirai dipole radar. And the blue circle shows the our mobile X-band dipole radar. This is the main observation tool for this study. So you can notice this time we showed very limited local convective activity with lightnings. So the background condition of the 2 campaigns in 2015, that was a strong El Nino event occurred. And this is a GS map rainfall distribution during the 2 months. And also here is a SST. This is a raw data, not anomaly, SST data. On the contrary, year 2017 was a weak La Nina condition. So some differences you can see, rainfall distribution and SST distribution too. So anyway, we got a very good MJO passage over the Sumatra island. In 2015, one MJO passed over Sumatra around here. This is a zonal wind component, and after the MJO onset, strong westerly wind passed over the Sumatra in the lower troposphere. On the other hand, so before that, there are many vital diurnal variation of the, for example, this is a theta E, and so on. On the other hand, year 2017, almost during strong westerly wind observed prevailed during the whole period. It is a little different between year 2015, even though there are 3 MJO passed over the Sumatra Island during this period. So anyway, we'd like to introduce a very interesting feature based on the BMKG surface observation. This is a day-to-day variation of the surface rainfall observed by automatic weather station, and its diurnal variation with color scales. So you can notice many open circles marked here. So this is a lightning reported by BMKG observer for SNOP and META report. So you can see every day, lightnings are observed for several hours in the afternoon to late early night before the onset of the MJO. And after then, there are some, you can see the several amount of rainfall even after the MJO onset, but completely no lightnings occurred after that. So this is consistent with a previous study. For example, Equatorial reported the heavy lightnings occurred not during the mature stage of the MJO, but the leading edge and after trailing edge there are many, much amount of the lightning observed, so that we expected to have much rainfall, no, much amount of lightnings in year 2017. But the result was completely different. This is also the day-to-day variation of the rainfall and lightnings with diurnal variation. So the diurnal variation of the rainfall in these panels are completely different. In 2015, very striking peak was observed in the evening, but year 2017, there was only a gentle peak around here. And even though the total amount of rainfall is not much different with that in 2015, but almost no lightning, even in inactive phase of the MJO passage over the inactive phase of the MJO around Sumatra Island. So what causes such differences? If we look at the vertical cross-section of echo coverage percentage and its diurnal variation among the 4 cases, MJO inactive period 2015 and active period. And there in 2017, what's that? Oh. So anyway, you can see clearly difference among MJO inactive period of the year 2015 and others. Only these cases, the convective echo top height more reaching about 15 kilometer high with vital followed by the vital stratiform region with specific diurnal variation. But in active period, there are not such high echo top at all. And if we see them in 2017, even in active period, such elevated echo top couldn't be seen. And if we check the local circulation, namely land sea breeze around Bengkulu city. So this is their diurnal variation, average diurnal variation of the sea breeze component in warm colors versus the cold color with northeasterly land breeze component. You can see all the case diurnal land breeze penetrated apparently observed in each case, but only in this MJO inactive phase of year 2015, very strong vertical shear is obvious because the background wind was northeasterly only in this case. And the other cases are the background wind was southwesterly. And atmospheric instability, namely Cape, showed its maximum with diurnal variability only in MJO inactive phase in 2015. It is in phase of the lightning frequency like this. So we can see such a vertical wind shear and atmospheric instability must be the one or two of the key points to form the vital lightning activity. So if we see the Cape inordinate and vertical wind shear between 500 meter to 6 kilometer. So the red square show the case in MJO inactive phase, and blue squares show that in MJO active phase with their averages with standard deviation. So you can see clearly they are divided with this line, this dashed line. Even that is subjectively I draw. But anyway, we can distinguish them very clearly. And the time series of the Cape and vertical wind shear also show the clear drop after the onset of the MGO active phase. On the contrary, they in year 2017, they didn't show such a clear difference between the MGO active and inactive phases. The time series also showed some zigzag patterns, but no clear difference between MGO active and inactive phase. So if we look at such a condition is located on only in the southwestern coast of Sumatra or other region. So this is a Urun lightning distribution during these two periods. So it is interesting that year 2015, we observed the very vital lightnings over Bengkulu city during the MJO inactive phase, but the lightning activity is very, very limited, located around the southwestern coast of Sumatra Island, and not much over the plain region, eastern side of the Bukit Barisan Mountains range. On the contrary, we couldn't see not much or completely no lightnings around Bengkulu city in 2017, but we found there are much amount of lightnings were occurred over the plain region over the eastern part of the mountain range, Bukit Barisan mountain range. So we have seen only a limited phenomena over this Bengkulu city in these two campaigns period. What makes these differences? So of course, the El Nino event and the La Nina event are one of the key points which produce such a background condition. You can see the previous study already showed such strong, how to say, vital lightnings observed in the southwestern coast of Sumatra in El Nino year, and La Nina year, they are moved in the eastern part of the Sumatra Island. That is consistent with our result too.
1 minute, Professor.
Oh, okay. And also, the local wind velocity and direction is important. But it are also show the 1 minute left, right?
Yes, yes.
Okay, I will conclude this.
Okay.
The location of the lightning, almost this side of the world is the main part of the lightning region. So if we check the environment wind by JLR 55 at 850 hectopascals minus and 1000 pascals, we can see clear such a vertical wind shear in 2015 over the coastal region, but that over the plain region, eastern part of the Bukit Barisan in year 2017. So the which suggests the direction of the vertical wind shear must be important. So as already Professor Courtney Schumacher introduced their recent paper, this image must be very.
Your time is up, Professor Mori. I'm sorry.
Okay. Okay, so this is a summary of the my talk, and thank you very much for your attention, and sorry for the extent of my time. Thank you.
No problem. Thank you very much, Professor Mori. So this is like a complete plenary session, yeah. Now we learn about lightnings. So this is very, very important topics. The next speaker, the last one, Dr. Wei Dong Yu from Sun Yat-sen University. Dr. Yu, are you there?
Yes, I'm
Yes.
here.
It's yours now, please.
Okay, thank you. I try to share the screen. Oh, sorry. So it seems it need some configuration here.
Okay.
So can you help open my PPT from your side? It seems my here is I need some configuration I'm not knowing quite well.
It's okay. The organizing committee, can you help?
Yes, please. So that's good.
Okay.
Thank you. Yeah, that's great. It's my pleasure to be given a chance to talk here. Yeah, we already hear a lot of discussion about a lot of MGO activity. I hear some echo, some strong echoes. Yeah, I'd like to talk about the MGO and also the Indonesia-Australia monsoon onset process. So it's the wet season for Indonesia is very important. So that is why I talk about how this kind of a wet season is established. And I'm mainly focused on or emphasize the role of intra-seasonal time scale, such as the role of MGO to trigger the Indonesia-Australia monsoon. And here I focus on the large scale summer hemisphere monsoon. So that is why I call it the Indonesia-Australia monsoon. This is a rainfall for the Boreal summer and the Austral summer monsoon. So you will see for the Austral summer monsoon, so that is Indonesia Australia monsoon is a large scale rainfall over the Java Island all the way to the northern Australian region. So this is for this region, I will focus to give you the process how the first eastward propagating MGO can trigger this Indonesia Australia monsoon. Next one, please. Next, please. Okay. This is a mean seasonal cycle. So the shaded is a SLT, the vector is a wind. And I draw your attention to the blue box over the Indonesia and the northern Australia. This is the region we focus here. I would like to draw your attention to the November and December. So you will see the Indonesia Australia monsoon is you can say from the vector wind, the westerly wind. Westerly wind is a representative signal for this monsoon regime. So westerly wind you will say is fully established during the December, and before the December we can see the November the SLT maximum already occurs between the Australia and Indonesia. So this maritime continent, the SLT, we will say is very much as leading the monsoon onset process. So this is one of the feature I would like to emphasize. We can see the monsoon onset from point of view of ocean atmosphere interaction. So next one, please. Yeah, this is again, this is a seasonal cycle. I just say have a 2 years seasonal cycle and draw your attention to before the monsoon onset over the maritime continent. You will say this is a SLT. The red curve is a SLT. The red curve is reaches the annual maximum. So that means the SIT maximum is one of the leading or preconditioning for this kind of monsoon onset. And after this monsoon onset, we see the SIT is drop, and we see the westerly wind is established, and the wet season is established. So it's very clearly the SIT is preconditioning condition for this maritime continental monsoon. Next, please. Yeah, I re-emphasize the role of SIT. So this is at a very much large scale Indo-Pacific region, so maximum SIT distribution, and the arrow indicates which month the maximum SIT occurs. So it's pointing north, it's December, and clockwise with the calendar month. So when we zoom into between the Indonesia and Australia, we can say the SIT maximum is around 30 degrees, and that occurs at the end of November to the early December. So we can understand this is a monsoon onset window for this area, and before the monsoon is established, we say the maximum SIT is fully established. So this is a precondition, oceanic precondition for monsoon onset. And if you look at the other regions for South Asia and South China Sea, it's a similar story. Before the monsoon onset, you will see for the Southern Asia, the SIT maximum is in the early May. So this is also before the monsoon onset. Is very well. They are very similar. The ocean precondition, the monsoon onset by the maximum SIT establishment there. Next one, please. Yeah. For this area, so we understand that there is a very strong interseasonal oscillation. So I give you one example. The last one is OIR, standard deviation. So when we focus on the DGF in the lower panel, we will see the maximum signal is over the maritime continent. So that is why for this area, the interseasonal oscillation is very important. And from an interseasonal point of view, I gather all the monsoon onset dates and project them onto this Hayden-Weyler diagram to show their MGO development. So we will say the different number indicates a year of a monsoon onset on that, the date of monsoon onset on that year, and in a corresponding MGO phase. So the block dot is a composite. So that means most of the monsoon onset occurs. Sorry, I see a strong echo here. Yeah, the monsoon onset is mainly occurred during the MGO.
Please unmute for other people. Unmute yourself.
Yes, I think so.
Please, the organizer, to unmute other people other than the speakers. Yes, please.
Okay, thank you. Thank you. It's much better.
Go in.
It's much better. Thank you. The answer is the answer. Okay, thank you. Thank you. So the video pass over this better.
Maybe connection in the organizing committee screen. Yes, the screen is just stays, remain stays. Maybe you can turn off the share screen and then doing the screen again, BMKG, because this is, the screen is from BMKG. It's okay, Dr. Su, we wait for the organization. Yes,
okay,
now it's
okay.
moving. Yep.
Yeah. This is a composite of the monsoon onset process. Is once again the shaded is the ST and the vector is the wind. So pay attention to the green color vector. So that is a westerly wind. So we use a westerly wind to indicate the monsoon onset over the maritime continent. So this is a time day zero. Day zero means the monsoon onset over the maritime continent region. So you will see the west wind is well established here. And before that, this is a day -10. So you would say before the monsoon onset, the ST over the maritime continent is very high, over 30 degrees. And after the monsoon onset here, so the contour is the OIR. So this deep convection system pass over the maritime continent and then establish the monsoon in that rear. And after that, we will see the ST is drop. So it's very clear the SIT maximum is established, and then the MGO is going over the maritime continent, and then westerly wind is established. The maritime continent monsoon is onset there. So next one, please. Yes, I give another way to show this monsoon onset. This is average. This is a meridionally average between the equator and the 15 degrees south, and we see the eastward propagating of MGO activity. Again, this vertical axis is date. The date zero means the monsoon onset over the maritime continent. And for corresponding to this maritime continent monsoon onset, we say before the monsoon onset, we already see the SST maximum established between the Indonesia and Australia. And then we have the deep convection system moving all the way forward to the eastward, pass over the maritime continent, going all the way to the Western Indian Ocean. So remember, this is the first MGO eastward propagating during the Boro winter season. And we know before that is the interseasonal oscillation is during its Boro summer season is a more strong northward propagation and not too much eastward propagation. And this is the first time a northward propagation is decay and the eastward propagation is very much enhanced. So it's very clear this is the first MGO and then followed by the second MGO sometimes later. And the first MGO is triggered the maritime continent monsoon there. And during this monsoon season, we see the westerly wind is very much steady and persist there for about 2 to 3 months time over the maritime continent. And this is one typical process for the monsoon onset over the maritime continent. Is the key feature is the SST leading there, and then favorable MGO eastward propagating over the maritime continent, and then west wind is very much established, and we can say the convection or wet phase is established for the maritime continent region. Next one, please. Next slide, please. Next slide. Yes, maybe you can ask a question, what is the relation between the SRT maximum and the first eastward propagating of MGO? So from point of view of convection instability, so we can say the left panel shows a plot of instability. We can say it's over the maritime continent. This is the maximum instability corresponding to this SRT maximum region. Yeah, and this is again the similar composite plot for the convection instability. So before the monsoon onset, we say is the maximum instability is very well established over the maritime continent, corresponding quite well from these the SRT maximum. And we can say this maximum SRT is favorable for this establishment of convection stability. And that is why this MGO is going forward and not anymore going to the northward.
Sorry,
so,
can you complete in 2 minutes? I know
yes.
there are a lot of interruption.
Yeah.
Yep,
So this is we can say the SRT really helps the eastward propagating of MGO. Next one, please. Yeah, this is I would like to show, this is a summary diagram to show you the relation between the SRT intra-seasonal oscillation and the monsoon onset process. So when we look at a large scale, the Asian Australian monsoon is they are follow the similar process. So before the monsoon onset, the SRT maximum is established over the corresponding region, the maritime continent and also the South Asia region. And then they favor a very strong convection instability and very much favor the intra-seasonal oscillation propagating. For the case of a Southern Asian monsoon, that is will attract the northward propagating ISO, and for this maritime continent, they will favor the eastward propagating of Mediterranean oscillation. So they are the similar story. Next one. So we re-emphasize this process by the insight observation by during this BMC project by deploying the buoy observation. Next one, please. Yes, next one, please. So this is just to show you the buoy deployment. So we will clearly say the MGO propagating 2 MGO event, and before that, we say clearly the SRT is already preconditioned. Next one, please. Next one, I skip it. Yeah, next one. Yeah, so I go to the summaries. For this maritime continent monsoon onset is very much preconditioned by the SRT maximum. And this SRT maximum is favor the eastward propagating of MGO by the convection instability. And so in that sense, it's the peak SRT, the first eastward propagating MGO, and also the monsoon onset is linked together through such kind of intra-seasonal oscillation. And we observe for the year 2018, 2019 for this Australian monsoon onset process. So I think I stop here. So it's not too much smoothly presentation. Sorry about that. Thank you.
Yes, thank you, Dr. Yu. We are also sorry for the technical difficulties, maybe because there are still participants who want to enter the room. So that's maybe causing some issues. I'm sorry for that one, Dr. Yu, but at least we already got the message from you about the Indo-Australian monsoon. We have to understand Indo-Australian monsoon so we can have a better understanding about the rainfall development in the tropic, particularly for Indonesia. So now it's a discussion session. I already see a lot of questions in the chat room. I don't know whether the organizer already extract the question and can show to the screen, because in the chat room it's not only a question but also another topics are bring about in the chat room. But at least I have see the first one is going to Dr. Sandro, and maybe all of you also the speaker already observed the chat room. Maybe we can start from Dr. Sandro first. Please, Dr. Sandro, can you answer the question related to your presentation with regards to Jakarta flooding? Please, Dr. Sandro. Dr. Sandro is still here. The next question will be from okay.
Hey, yeah,
Dr. Sandro here. Yes, go ahead.
Right, I got a question from I think from you. So he's asking about whether the Kelvin wave contribute to the flooding event that we have recently in January 2020. So the answer is yes. So we look at the data and we filter for different tropical wave types during the event. So we found that there are two indications that the Kelvin waves and also the Equatorial Rossby wave contribute to the events. But like I said in the comments, it is not the only factors. We also see there is a formation of the cyclonic system of the southern part of the Java Islands that probably can also contribute to the moistening of the air over the Jakarta that favor for the convection of these regions. So the result that we have is not complete. So we are just started the study. So we also try to look at the implication for the Borneo vortex over the chance if there is other factor that contributing to the flooding event during this event. But what we are working now is really focused on the MGO and the tropical wave only. So we really want to address if the flooding in Jakarta are attributed also by the equatorial wave.
Thank you, Dr. Sandro. Another question is from Mr. Jun Matsumoto to Dr. Muteki. Can you explain about the cold surge and the attribute of the cyclone to the active MGO? Please, Dr. Muteki.
Yes, thank you very much for.
You also can answer another question, yeah, related to the sense over Jakarta.
Okay.
Yep.
Thank you very much for a very nice question, Professor Matsumoto. Actually, the role of twin cyclones in the Western Pacific on Sense 6 will be very, very important issue to be addressed. I just imagine that the pressure gradient falls around the twin cyclone, because the twin cyclone has a little bit low pressure, local minimum of the low pressure. So there are, the pressure gradient force is worked around there. And so that would enhance the surge flow. So that should be the important issues. But I haven't yet addressed it in detail yet. Thanks for comment.
Okay, and in here I also see Muri Sensei provide some explanation about the question. Please, can you explain more here, Professor Muri?
Okay, as I already made a comment in the chat room, yes, Professor Matsumoto asked me about the source or importance of the northeaster wind against the other environmental condition for form the vital lightning activity over the western part of the southwestern part of the Sumatra Island. Yes, he suggested me that the MJO is the important source. Yes, I suppose location of the MJO was important, but the originally I suppose the yes, cross-equatorial northerly search sense must be the one of the more important source to produce the background northeasterly above the 850 Pascal. Thank you.
Okay, thank you, Professor Mori. Is there any more question from the chat box or want to raise hand from the participant? If not, I will provide the speaker who want to just jump in and addressing the question or strengthening the answers. Please, maybe we can start from Professor Scott Glenn. You want to add more? Because there are a lot of discussion about the ocean here, ocean phenomena, SST and so on. Please, Professor Scott Glenn.
I was impressed by Jidong's talk about the maritime continent being a wonderful place to look at the land, sea differences, and how that impacts the weather in that area. So that was one of the places that I was thinking of commenting about. We have other places in other, like the Caribbean Sea, which would benefit from what you learn here in the maritime continent, and we can use that for our hurricane work there. So thank you for that talk, Chidong.
Yep. Thank you, Professor Glenn, because in here, even we attended the conferences, the most important thing is how we can establish a connection and collaboration research, yeah? So thank you, Professor Glenn, for your response. And maybe I see in the chat room, Dr. Yu want to comment? Please, Dr. Yu.
Yes, thank you. I just want to emphasize is VMC is very much a successful project for this maritime continent region, but looking into the next decades is the UN Ocean Decade is the next 10 years. So I would like to ask the VMC committee, many members are here, particularly Chidong and also James, their colleagues, do VMC would like to continue some kind of legacy into the UN decade. So what is the next decadal vision following up the VMC? So this is a very critical region. I would like to have more feedback from the audience. Thank you.
Thank you. So your name is called many times, Professor Dr. Sidong Zong. Can you respond, Dr. Zhang?
Yes, can you hear me?
Yes.
Yeah, I appreciate the comments from Scott and Wei Dong. Yes, it's absolutely correct that even though I think the maritime continent is the best place to study the coastal transition zone, there's many other places in the world that the concept can also apply. And following Wei Dong's comment that it's not just the YMC, I think the entire region should pay more attention to this new UN decades, especially UN decades of ocean, especially those activities related to the coastal area. And I think this unique area provide many opportunities to spear ahead new research activities focus on coastal ocean, marginal ocean, and ocean-land Aeros interaction. So I hope the leadership of BMKG and Indonesia and other countries will recognize this opportunity and importance and continue support research, not only within Indonesia and BMKG, and just like this, support international collaboration and interaction. And we hope the ongoing YMC and other international research in this area will continue for many years to come. Thank you.
Yep. Thank you, Dr. Zong. Please, Professor Sumaker, can you just jump into it? Because I see your questioning about KBO impact.
Yeah, this is for Mori-san. And I was curious because you had been talking about MJO impacts on lightning and depth of convection and shear and things like that. I didn't know if you looked at the QBO because that's sort of a hot topic. QBO and MJO interactions.
I should do. Tell the truth, I haven't checked it. And for the future study or current study, I should check the QBO status too. That is recently very important issue for the not only the tropical but also the extratropical region, include Japanese heavy rainfall. Yes, thank you.
Yeah, no, and I appreciate it. It was only two. You might be in the same phase even, but it would be interesting to look. And I appreciate you trying to show a picture from Chu's paper at the end. In terms of the shear, I'd like to hear more about that later.
Thank you.
Okay, thank you, Professor Sumaker. Maybe the last one I want to hear again from Professor Hong. Dr. Hong, are you there? Because land climate interaction, atmosphere, ocean is huge. And Dr. Hong is talking more about model improvement, right? You're talking more about the key up forecast skill, how this can help you on, something like that. Please, can you comment? Dr. Hong, are you still there? We have to complete by 10:15 and we still have a time. Is there any more question?
Could you repeat the question?
Yeah, we already talked about the importance of the land, land, ocean, atmosphere interaction to further understand the Earth system of climate interaction scheme. And you are working for the model development, right? The KEEPS. Can you what you learned from this discussion and share to the audience? Can you comment on that?
What's the last word? I get it. It was disconnected. What is the last word, sentence?
So, can you comment on how you can further advance your model development after learning the complexity of the situation from one climate phenomena to the others?
Yeah, I think for climate, I think it is important to share the finding with the numerical weather prediction community.
Mm-hmm.
So I think for climate, there is a divergence, so that there are uncertainty is accumulated. We don't know how to improve it. So that is, I think for short-range forecast, we can approach by a different aspect. And then we can share these revisions with the climate community and the weather prediction communities.
Okay. Yeah. Thank you, Professor. We are near our time. It's already 10:07. So maybe I want to share my screen to If there is still additional discussion, maybe you want to shoot on. And also for the participant, you still can try to pose your question, yeah. So for this international conference, I moderated the discussion from the very distinguished professors, yeah, from around the world, I can say, because this is starting from the north to the east, right? My name is once again Ferdinand with letter P, yeah. If you Google me, it's with letter P, not F, Ferdinand. So graduated from geography, my master degree in resource economics. So maybe very far from you guys. But my bachelor degree similar with Sandro from IPB in meteorology. I'm an associate professor of IPB University, and now I'm board director of Seong Yoo Biotrop. We want to have a new topic on how we can understand weather, climate, on tropical biodiversity. So this is what you guys discuss for this nice over 2 hours, I think 2 hours talk. Actually, we want to understand rainfall dynamics, starting from development process, extreme events, spatial formation, diurnal pattern, started from Dr. Sandro, who are talking about the mesoscale analysis on equatorial wave, how the equatorial wave can somehow moderate the rainfall dynamic in the tropic. And then follow up by Professor Glenn, that is talking more leaning toward cyclone formation and stressing the important to understand ocean heat potential. And then Professor Schumacher is very nicely discussed to add additional factor that we have to understand, that is the land influence, how the topographical effects can somehow affect the rainfall dynamic, particularly over the diurnal pattern. Dr. Hong bring us to another venue. This complexity can be modeled. The KIAPS is now still undergoing, how we can improve our forecast skill by understanding all the components of the Earth climate system. And then Professor Zong provide a nice idea about the coastal transition zone. We need to understand land, ocean, air interaction better, because this complexity of Earth climate system, there are still a lot of questions we have to answer. And by combining the observation of land, ocean, and air, and maybe also the forecast, the modeling part, like what Professor Hong did, we can better understand about this complex issue. The next three speakers, Dr. Moteki, Dr. Mori, and Dr. Yu, are explaining about the fact and evidence. Air mass dynamic, how about the cold surge effect, particularly in the tropics? Lightning, how this lightning formation and so on interplay with the NGO effects. And close by Dr. Yu, Indo-Australia monsoon events, how this climate phenomena controlling the monsoon as critical factors that governing rainfall dynamics in the tropic. So this is really answer nicely the conference theme, International Conference on Tropical Meteorology and Atmospheric Science. So this is really enhancing, improving our knowledge and understanding about tropical meteorology. So even you guys are from the subtropical countries, thank you very much to let us understand better about our tropical areas. For those who are interested, each note I also provide in this slide from Dr. Sandro, talking mostly convergent and convection dynamic, Rossby and Kelvin wave, from Professor Scott Glenn, disasters. So because I'm also very close with Natural Disaster Management Agency of Indonesia, so we are very thankful for today talks. impact of the ocean head potential, intensity of the wind speed, and the improve of models forecast for land location. So here talking about land interaction. From Professor Schumacher, stratiform rainfall associated with convective process, we have to better understand because this is influenced by the topographical effect. We can study from the zonal moisture. BMKG have the radar and cluster analysis can be used. Dr. Seong Yoo Hong, this is complex issues, development of atmospheric model to improve the forecast skill, particularly provide the better understanding on the heavy rainfall. And Dr. Sidong Zhang, coastal transition zone. This is very like a frontier ideas, yeah, how we can understand the interface from surface freshwater to saltwater and the effect of transition zone. So we can like do a combination observation, ocean, land, atmosphere to understand the Earth climate system. Dr. Moteki Mori, Dr. Mori, and Dr. Wei Dong Yu provide the fact and evidence how we really need to understand all these complex issues because we need waters. Dr. Moteki say the features of cold surge event and the effect of the cold surge to air dynamic in modifying rainfall development, follow up by Dr. Mori Suichi, climate phenomena and so MGO effect to the frequency of lightning, because we know when the lightning occurs, usually also followed by the rainfall. Synoptic scale of zonal wind, ecotop, and land sea breeze events. So we can better understand about this issue. And close by Dr. Wei Dong Yu, even though we found some difficulties, technical difficulty, we are very sorry for that one, Dr. Wei Dong Yu. But the SST dynamic to learn monsoon event is very important because, you know, like for example, in Indonesia, our rainfall is strongly affected by the monsoonal event. Maybe that's what I can do the summarize as now already 10:14 and we only have 1 minute left. If there any close comment or whatever you want to say, please do so. Is there any last comment from the speakers?
This is Chidong Zhang. I just like
Yes.
to thank Professor Pedinan for organizing this session, and I would like to thank BMKG for organizing this workshop.
Likewise. It was a pleasure.
Same from me.
I try to share the notes in the chat room, yeah, so everybody can download, and if there is maybe some revision you want to make, please do so we can have a better report about what we really learned from this talk today. So if there is no other question or comments, maybe I will give a time to the host of this meeting conference. BMKG. Ya,
Thank
Ibu
you.
Niluh ya, Niluh Janita. Silakan, Mbak.
Thank you, Dr. Ferdinand, for guiding this session. And also, we like to thank to the speakers for sharing with us your knowledge and expertise. Coming up, next agenda is parallel sessions, but before it, we would like to invite the moderator, speakers, and participants to turn on your camera as we will have to start the photo session.
This is the last session that we are waiting, yeah?
Yeah. So please, for all the speakers, moderator, and participants, you may turn on your camera. We will start from the page 1. Get ready, everyone.
Yeah. It seems my camera could not open.
Yeah. Sandro dapat salam dari Bu Tania ya.
Get ready, everyone.
Yep.
From page 1, say cheers.
Cheers.
Thank you.
Finally, we can say cheers after the pandemic situation. Yeah, usually we use masker, right?
Next,
okay.
Page 2. Get ready, everyone. You may smile too. Thank you. For next, page 3. Get ready. Wonderful. And 4.
I think this good lah. From Professor Muteki. We need something as like indicating that we are meeting next time. Like
Thank
this one
you.
or this
Second,
one.
And page
Okay.
5. Oh, okay. We kindly ask you to raise your thumbs and give a big smile. Okay, right?
Right.
Get ready, everyone.
Yeah.
1, 2, 3.
Yeah.
Okay, thank
At
you.
Diatrop, we do this to support education. We do the campaign worldwide to support education by raising your hand like this one.
Okay, for the last photo.
Yeah.
Get ready, everyone.
Yep.
Thank you so much. Wonderful.
Thank you so much. Thank you. And I might leave this conference room, yeah.
Thank
Everybody.
you so much, Dr.
Yeah.
Ferdinand.
Yeah, thank you,
For
everybody.
parallel session, we will be shared in 5 rooms that we have provided just for you. You may click on the breakout menu and choose the rooms to join the parallel session. I would also encourage the participants to visit poster presentation room in ICTMAS website. And for the reminder, please be noted that our closing ceremony will be begin at 12 local time in Jakarta. Please make sure to follow till the end of the event because there will be the announcement for the best posters and best oral presentation. Thank you.
Oke, Bapak ya. Saya lihat ada Prof. Edi itu. Saya pamit duluan ya. Bye-bye, Profesor Muteki. I have another meeting. Bye.
Being the largest maritime country in the world, we are aware of the importance of our ocean in influencing the world's weather and climate, especially the influence of the Indonesia through flow connected between the Indian and Pacific Ocean to the weather and climate states in the world. Indonesia, through the Agency for Meteorology, Climatology and Geophysics, BMKG, is strongly committed to contribute to the safety of human activities and community welfare by continuously educating people on the importance of ocean weather climate literacy and sustaining our observation and keep strengthening our provision of the accurate maritime weather and climate information, as well as early warning of the coastal disaster information such as storm surge, tsunami, and sea level rise to the community in Indonesia and in the region. Meteorological Day of 2021. Let's strengthen our partnership for the better ocean weather climate information.
Robek lah sana. Pati robekin nih.